Chapter 18, Part 2. Part 2. There you go. All right, we've just been going over all sorts of sort of baseline stuff here in terms of how to think about enols and enolates and relative reactivity and self-condensation. We haven't used that term yet. But let me start by complaining about the book. That's a very dangerous thing. I've learned in organic chemistry is you shouldn't complain about the book because people think there's something, why are we using a bad book? Well, it's not a bad book. I actually like this book in a lot of ways. But if you look at page 817, wow, think of how far you've come. There's a reaction just depicted that looks like this. With a base. All right, this is not exactly the way it's shown, but it's pretty close. What's wrong with that? What's wrong with it is we are looking down on a carbonyl. The p orbitals are above and below the plane of the paper. You're looking down on the p top, or up at the bottom of the p orbitals. And this hydrogen is bonded to a carbon through an sp3 hybridized bond, and that bond is very clearly written to be in the same plane as everything else over on the right hand side of the molecule. This is wrong. Okay, although it's easy to draw it that way, this should be a hydrogen that is up, and then you could, if you wanted to, bring both of those down. But, fundamentally, if you want this acid-base reaction to occur, I suppose I should do this. You need to have this sp3 carbon hydrogen bond to line up with the p orbitals. Right? So this is why if you have cyclohexenone, which is pretty planar, the vinyl proton here next to the carbonyl is not acidic. You cannot pull that proton off with base. Doesn't matter how strong the base is. The acidic protons are these two alpha, and these two, which are alpha, beta, gamma. Those are the ones that if you take this and you treat it with D2O, you put it in D2O with a little sodium deuteroxide, you will reversibly pull off the acidic protons, and you will per-deuterate, meaning you will fully substitute all of the acidic protons with deuterium, and you will put two of them over here, and you'll put two of them over here, and that will be it. Okay. So, just recognize that this depiction in your book doesn't properly show you orbital overlap and that's a problem. If you look in, I haven't done this, not recently, but if you look in Jones and Fleming, which is a really good book, and so from Maitland Jones, who is a very revered organic chemist and teacher at Princeton University, who wrote the first version of the book, and Stephen Fleming, who you will find wandering around the chemistry department sometimes, or actually mostly in his office. Stephen Fleming, Professor Stephen Fleming, who's really the only author now of this. This is a really good book, and it's very orbital centric, so I'm sure that they depict this properly. Just wanted to make sure you understood that. Okay, so we know, and you should know, that if you have a stereogenic center, alpha to a ketone, like this. Let's talk about 2-methylcyclohexanone. It's really, in terms of illustrating organic reactivity in many aspects, this will not be the last time you see this. 2-methylcyclohexanone is really great one to talk about. As I have it drawn here, I'm sure you've already figured out this is the R. Right? 1, 2, 3. Hydrogen is back. If you treat this with hydroxide, yeah, it'll add reversibly to carbonyl, but that's it'll deprotonate these hydrogens. It'll also deprotonate this hydrogen. Or you put an acid, you will reversibly form an enol, which is either an enol or an enolate, and that's reversible. And when you do that, you've destroyed the stereochemistry. And I'll just draw it this way. If you had prepared this carefully and made it R, and there are ways to do that, if you treat it with acid or base, you will racemize this stereocenter, because this stereocenter is a polymerizable. And you'll find that term in your textbook. So, because proton off, proton on, and so that's something to be concerned about in some cases. It's also something that can be useful. And let me give you an example, and I'm going to start on the clean page to talk a little bit about one of the demigods of organic chemistry, R.B. Woodward, Robert Burns Woodward, which I may have mentioned earlier. 1964, got the Nobel Prize for art in organic synthesis. There's a ton of stuff online. I was fortunate enough to meet and talk to Woodward a couple of times as a graduate student. One of his seminal contributions was making a steroid, and I believe this was published in 1952. All right, there's your standard steroid nucleus, if you will. And steroids almost always have a stereogenic center here, a chiral center that's got a methyl substituent that's up, and another methyl group here. and then they're generally trans, 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 trans in their ring juncture, and trans again if there is a stereogenic center there. All right, so that's a steroid, and many of them, including cortisone and things like testosterone and cholesterol, all have a long chain substituent here, and a couple that gives them a couple more stereogenic centers. And if you draw it this way, again, it's trans. No stereo center here, of course. That's kind of your standard steroid. The seminal contribution that he made, and I'm leading up to a couple of things that I think you be partly review, but also not. Now this one does have, except a shortened side chain. This one has a ketone here. Ketone here and enone over here. And there's an alcohol here and there's an alcohol here, and so here's a dihydroxyketone. This is called, and a ketone here, that's really important, cortisone, which is, in my lifetime, has gone from a prescription-only drug to an over-the-counter drug, but you have to be careful with steroids because you take too much cortisone and your skin thins, and there's lots and lots of reactions. Well, Woodward published a lengthy but very elegant synthesis of cortisone that starts with a paraquinone. Quinones look like this, obviously, because you can also have an orthoquinone. Argue this is semi-aromatic, and this one, the one he used, had a methoxy group at this position, which makes this a vinylogous ester, say ester-like, which means it's more stabilized than the enone on the other side here, and has a methyl group. And he brings this together with butadiene, which of course is, I'm drawing in the S-cis conformation, but it's mostly S-trans, S of course being the single bond that we're talking about when we're talking about conjugated dienes. But this is not a reactive form. The minor component of this equilibrium, the S-cis, is, and this undergoes a Diels-Alder reaction. This is review, but it only will react over here, and there's no substitution on this butadiene, so there's no question about relative regioselectivity, right? So if this had a methyl group, it could be on this end or that end. We don't have to worry about that. Here's so we retain all of this, but you get a new ring, and of course, because as I'm showing it here, the diene is coming in from the bottom face. There, as I said, there's no substitution on the diene, so there's no regioselectivity. There's also no way of telling endo or exo. We know we probably get both, mostly the endo. You can't tell that because we do not have any stereochemistry here that would be revealed, the revealing feature showing you endo or exo. All right, so that's the first step. And so now we've got two rings. Interestingly, this component this product eventually becomes, this is A, B, C, and D. So this becomes the CD ring. So he's put in this quaternary carbon with this reaction, but he's got the wrong stereochemistry. Now, he knows, now this is 1952, or actually late 40s when he's really starting to work on this, that decalin. So decalin is the 10 carbon bicyclic 6,6 fused ring system, and you can have cis and trans. So here's the cis, and here's the trans decalin. And if you don't remember cis and trans decalins, they are in your textbook. All right. Now, one thing we know is that lower in energy. Okay, that the trans decalin is more stable than the cis decalin. Now you can think about it this way. Because a cis decalin, which is, I've just drawn the wrong stereochemistry here because these hydrogens are down the way I look at it. But we have an axial carbon here on this ring, and we have, whereas this one is equatorial. Sorry, axial here on this ring, and this is axial on the other ring. Okay, so, and if you have the trans, everything's equatorial. Right, so if you had decalone, and you treat this, if you have the cis decalone, and you treat this with hydroxide, you will epimerize this center, and that's reversible, and only this stereo center here. And it'll mostly funnel over to trans-decalone. Decalone. So Woodward knew that, and so he did the Diels-Alder reaction to get these two stereos, to get this bicyclic system, and then he treats it with sodium hydroxide. And to his utter dismay, no doubt, trying to epimerize it to what he assumed would be the more stable compound, there is an equilibrium, but it's mostly over on the side of his starting material for this reaction. So this epimerization does not work. Why doesn't it not work? Well, you know, look, this is a very different molecule. This whole part over here is flat. You've got a flat molecule over here. He could build models and look at them, but this was, again, 1940s. There were ways of doing calculations, but they're not trivial like they are today. So, he eventually figures out that this product that he's looking for is a solid, and that he can take and do this equilibration and dump in acid and stop that equilibration, and then by removing the base, and then put a seed of the product he wants and crystallizing out the isomer he wants. So that's called hard work, but also very gifted chemistry, and he has four postdocs and graduate students on this paper as well. They worked like dogs to get this done. All right, so that is, I think, a lovely illustration of the ability to set stereochemistry with the Diels-Alder reaction, and also use epimerization to change one of those stereocenters. Now, of course, cortisone is a natural product. It's a single enantiomer. This Diels-Alder reaction is racemic. That's just the way the total synthesis went. So anyway, I think this is we're over time here, and we'll get back to more chapter 18 stuff momentarily.